So the last section tonight is section 6.2. Now, if you notice, when I write my section numbers, I always write it kind of with this integral sign. And the inside joke for me when I teach my algebra classes is I still do the same thing, except nobody gets it. So it's my little joke on them. Yeah, you get it. My SI gets it. A little bit of history here for you. The integral symbol is actually notation that came from Leibniz. Now, Leibniz developed calculus at the same time that Newton did, except that Newton didn't publish his. He just kind of kept it secret. He was very secretive of a lot of his research. So he didn't publish it. And actually Leibniz was a little bit later in coming out with his, but when he came out with it, there was a big feud over who invented calculus. And it really set things back for a while because there was such a big row about it. But Leibniz notation survives. Interestingly enough, though, and I don't know why this is true, if you look at Newton's house, you can Google a picture of Newton's house, it looks like there's an integral symbol on it. It's as if Leibniz has the last laugh. Although, has anyone ever heard of Leibniz? All right, not much more than you've heard right here. All right, so section 6.2, we're going to solve differential equations. Let's do a friendly one to start with. That's problem number 2. So dy by dx equals 5 minus 8x. Now this is kind of like what we saw in a previous section, where you want to get the x's and y's by themselves. Here it's pretty easy. If you multiply both sides by dx, wow, you get the y's and the x's separated. So, wow, that's pretty nice. To finish solving then, what do you suppose I have to do? Not all at once. Make me look good. This is on video, right? There you go. Thank you. Integrate both sides. Was that Todd? Thank you. So we'll integrate both sides. On the left-hand side, you get y. Technically, you get y plus a constant. We'll deal with the constant on the right-hand side. How about the integral of the right-hand side? What's that going to give us? 5x minus 4x squared. And here's where you got your constant. Woohoo!
That was easy.
Put a dozen of those on the exam, right? That's it. That's all there is to it. Now, it does get a little bit more involved when we have to do more work to separate the variables or to solve for y, but that one, that's it. Let's try one that's a little bit more challenging. That's problem number 4. dy equals dx, or dy by dx equals 6 minus y. Like the last one, I'm going to start by getting rid of the fraction here in the differential. So multiply both sides by dx. And then what? Well, I don't have the y's and the x's on their own side yet. So I'll divide both sides by this 6 minus y term. dy over 6 minus y equals dx. Well, at least now I've got things separated here. So let's see what we can do. So, Rand, what should I do here to continue solving? Hint. Integrate. So I'm going to integrate on both sides. What am I integrating on the right-hand side? 1. Essentially, you're integrating 1. It's not really written, but it's understood that there's a 1 there. So the integral of 1 is just going to be x. But somebody should be busting my chops on something. X plus your constant of integration. We need that there. On the left-hand side, what are we going to do to integrate the left-hand side? Good question. We can't separate this because it's in the denominator. You could bring it up with a negative exponent, but it's not really going to change the work that you have to do. U substitution, okay. What should I let U equal? U equals 6 minus y. Du by dy would be -1, or du equals negative dy. Okay. Let's put the negative on the left-hand side. Negative du equals dy. Let's see if we made ourselves any progress. That's the integral of negative du over u. Did that help us out at all? Yes. What's the antiderivative of this? Natural log. So this is going to be minus the natural log of the absolute value of u equals x plus c, or minus ln of 6 minus y equals x plus c. Okay. But we're going to take a step to solve for y in this case. I want to get y by itself. So I'll multiply both sides by -1, and I get negative x. Technically, it'd be negative x minus c, but we're going to abuse our constants. Minus a constant is still a constant. If it's really bothering you, you can think of this as constant 1 and this is constant 2. But it's still a constant. It's just negative of what it was originally. It's still a constant. The big challenge is to get rid of that logarithm. How can I get rid of the logarithm? What's the opposite of taking a log? What would undo a logarithm? Exponentiate. Good job. So I'll do e to the ln of 6 minus y equals e to negative x plus our constant. Now it's important that we had that constant here because it's going to come into play. On the left-hand side, these things are going to cancel. We're just going to be left with 6 minus y. On the right-hand side, I'll have e to the negative x. I'm going to write that as times e to the c. Yes. Now this is a constant to the power of a constant. Guess what? A constant to a constant. Kevin likes this one. It's another constant. So it's c times e to the negative x. Now, if you like I said, you can label these things different. You could say, all right, well, that's C2. Now this is C3. Fine. Bottom line is it's still a constant. I'm just going to call it C. I'm not going to worry about differentiating them from one another. It's still a constant. I want to solve for y. So I'm going to make kind of a little sleight of hand here. I've got a negative y here. If I move that y to the right-hand side, it changes sides and it also changes signs. So I'll get a y here. And then I'll move this to the left-hand side. And in a similar way, it's going to change signs. So I'll get 6 minus a constant e to the negative x. And if you wanted to, you could even write that as a plus because it's still a constant. So 6 minus or 6 plus doesn't matter. That last one. It's still a constant. But now you've solved for y. And that's where I wanted to get to, is actually solving for y. So you've got a exponential decay or growth model depending on the value of x. So there's a couple steps in there that might have gotten a little bit tricky in getting down to this last bit here. So if there's something that you'd like to go back and look at for a second, give me a shout out. So let me kind of put those two things together here. Could you do something like this for yourself on an exam? Hopefully the answer is yes, or hopefully you can spend a little time thinking about this and working with this to get there. Because we're going to do some more work with our exponential functions like this in this section. These kind of models come up quite often. They'll come up in exponential growth, like compound interest, population growth, or in decay, like radioactive decay. So these models are quite prevalent. But if there's nothing else, then yeah, Brandon?
So the constant, you could plus or minus it at any time?
Yeah, I mean, if it's, if it was a positive 7 here, it's going to be a negative 7 here. If it's a negative 7 here, it's going to be a positive 7 here. It's still a constant. And what's going to happen is that eventually you'll be given some initial conditions. They'll tell you that, when x is 0, y is 12 or something like that. And so if you have a minus sign here, when you solve, maybe you'll get a plus 8. If you had a plus sign here, maybe you'd solve and you get a minus 8. But you'd still end up with the same function either way. Yeah. Anything else on number 4?
Why do you bring down the C's?
Here? Okay, because I have E, which is a constant, to another constant. So a constant to a constant, and that's where this constant came from. So usually I'm in the habit of just writing it C and C and C and C. You could, technically, this is a different constant over here when you moved it to the other side. Well, I guess since I changed the sign, there you go. Now it's a different constant. Make it a plus. All right, so C4 is just opposite of what C3 was. One more? Yeah, please. It's not necessarily to isolate the dx, it's to get the x's by themselves. So if you look back in the first one, when I multiplied both sides by the x, I had the x's here and the y's here. So then I integrated. Here, when I multiplied through by dx, I didn't have the x's and y's by themselves until I divided out this term. Once I divided out that term, and I had the y's over here and the x's over here, that's when I integrated. Is that when you had them separated. Okay? So appreciate the question there. Okay. Let's try problem number 10. xy plus y prime equals 100x. What's a different way to write y prime? 100x, thank you, yes. Yeah, dy dx. So another way to view this one is xy plus dy dx equals 100x. I'm going to start by moving the xy term to the right-hand side. dy by dx is 100x minus xy. Okay, but I got some more work to do. As we just said, we want to get the x's and the y's on separate sides. So some suggestions. What can I do? All right, good. Let's factor out an x. So it's going to be 100 minus y times x. All right, that's good. Nice job. I didn't expect you to get that one just yet, but you did. Continue. I'm not sure I divide by x. All right, let's multiply by dx. X dx. And we're getting closer. We still don't have x's and y's separate yet, though. So Exactly. So to get rid of the y from the right-hand side, you can divide both sides by 100 minus y. So that'll give you dy over 100 minus y equals x dx. We're going to do pretty much the same thing here that we did just a minute ago. We're going to finish this one up by integrating. So integrate both sides. And in as much as it's late at night and I know you're tired, I'll help you out. I'll do the right-hand side, okay? All right. There. Cool. So you're halfway done with this. Work on the left-hand side. What are you going to have to do the left-hand side? Yeah. Do a little u substitution. U equals 100 minus y. So du is going to be a minus dy. And we can make our little u substitution from there. So I'm going to bring this back up a little bit on the page so I can kind of keep writing on this page. So this integral is going to become the integral of negative du over u equals x squared over 2 plus constant. Wakey, wakey. There you go. I guess I should have multiplied both sides by negative down here. Minus du equals dy. So that's where I got the negative as part of the du. What's the integral of this? Good. So yeah, that's minus ln of 100 minus y equals x squared over 2 plus c. So the integration part is something that I expect that you can work with, but what I want to give you a chance to spend a moment or two with is solving for y here. So kind of like the last one, you want to exponentiate both sides. Mimi and I will walk around, try and help out, but give that one a shot. And if you get it, great. Help out a neighbor. If you're struggling, try and catch our attention or talk to a neighbor. negative c. I'm not going to have a negative c. I'm just going to write it as c, but it'll all come out the wash. Okay. Okay. Yeah. Yeah. So to get rid of the log here, I'm going to exponentiate both sides. So it's going to be e to this power. Actually, you know what? Before I do that, I'm going to multiply both sides by a negative. So I'll get ln of the absolute value of 100 minus y equals negative x squared over 2 minus c plus c. Doesn't matter. But now I'm going to exponentiate both sides. I wanted to get rid of that negative first so that this will cancel out nice and evenly. It's not going to cancel out so cleanly if I have that negative out in front here. This cancels down to 100 minus y equals e to the negative x squared over 2 plus a constant. That can be rewritten as e to the negative x squared over 2 times e to the c. So you've got a constant to a constant. And a constant to a constant is a constant. So this thing here is just replaced by c here. E to the negative x squared over 2. 100 minus y. Last but not least, I'm going to swap these around and get 100 minus c e to the negative x squared over 2 equals y. Whew! How many people got that one? You know, depending on how you did it, you can have a plus c here, plus c, minus c, doesn't matter. You do need to have the negative in the exponent. So it has to be negative x squared over 2. All right, good job. Kind of following along that same line, let's do problem number 20. And you can see maybe how and why some of these formulas come up again and again and again. So you've got the rate of change of p is proportional to p. So that actually is a mathematical statement. We can translate that and have to translate that into words. So let's do that. The rate of change of p. How can I denote the rate of change of p? Yeah, dp dt. Good. So dp dt. That's problem number 20. dp dt is proportional to p. So the is proportional gives you a k, and then there's your p. This can be applied to a lot of different situations. Population. How much change there is depends on how many people there are. I mean, you're not going to grow by 1 billion people if you've only got 1 million. It's kind of tough. So your rate of change is proportional to what's there already. Now solving for this is another example of the problems that we've been doing. So dp equals kp dt. I want to get rid of the p here, so I'll divide both sides by p. dp over p equals k dt. What we're going to get out of this is the exponential growth model. I think it's called the Malthusian growth model, but don't quote me on that. We can now integrate this with respect to both sides. And what you're going to get is a model that you've seen with calculating continuously compounded interest or population growth. On the left-hand side, I get the natural log of p. On the right-hand side, well, keep in mind that k is a constant. What do I get when I integrate the right-hand side? Just t. It's not written, but it's understood that there's a 1 there. Sorry, appreciate the effort, thanks. So that's going to be k times t plus a constant. Now we're back to what I'm hoping is familiar territory. At least I'm trying to give you a chance to get comfortable with this because this is the third example in a row just like this. Exponentiate both sides. Left-hand side, I get P. The right-hand side is going to be e to the kt times e to the c. And by now, I'm hoping we're familiar with what happens there. C e to the kt. Now what happens is that this is your initial population or your initial amount. Initial amount. Maybe you're talking about investments that get continuously compounded interest. This is the growth rate or interest rate, and T is time. And this is your final amount. So you see this kind of a formula in your algebra classes and your college algebra and beginning algebra. But here's the actual derivation of that formula. Similar kinds of things will give you Newton's law of cooling, but there's a little bit more here. It tells us when T is 0, P is 5,000. So T equals 0, P equals 5,000. Let's plug that into our model. P equals C e to the kt. Okay. So if I plug in a 0 for T, C e to the k times 0, I get 5,000 for P. What's that telling me? Yes, C is 5,000. Let's see, let's do it here. All right, so C is 5,000. So my model, I can update it a little bit. It's P equals 5,000 e to the kt. Great. Tells me something else. Tells me that P is 4,750 when T is 1. So T equals 1, P is 4,750. If you take a look at things, what that's going to allow us to do is solve for K. Because we'll know what T is, we'll know what P is. The only unknown would be K. 4,750 equals 5,000 e to the k times 1, or 4,750 equals 5,000 e to the k. If this were me solving this, I'd divide everything by 4,750, or excuse me, no, by 5,000. So 4,750 divided by 5,000 equals e to the k. Almost done. How are you going to solve for k here? L on both sides. Good. ln 4,750. And I got to say, I'm impressed. I mean, it's pretty late at night, and you got that one right away. Equals k. So let's figure this out. I'm guessing that k is going to be negative. Why? Because after 1 year, 1 unit, 1 hour, whatever this time period is, your population or initial amount decreased. So it's not growing exponentially, it's decreasing exponentially. So I expected a negative value for k. Let's see if that's true. So ln of 4,750 divided by 5,000, negative 5.1. So k equals negative 0.05129, etc., or about a negative 5.13% growth rate. Your final answer should look like this. P equals 5,000 e to the negative 0.0513 t. Nice. They gave that to you in the problem, yeah. So if you look back, they tell you that at time equal 1, P is 4750. And that's what allowed us to solve for K. Okay. So the nice thing now is that you can make projections. If this was your population, maybe it's a population of a small town, you can figure out what the population is going to be 10 years out. Just plug in T equals 10. So there's this English professor got really mad at one of her students because he kept on text messaging and said, "You, give me 2 pronouns." And the student said, "Who? Me?" All right. Come on. Don't forget to tip your servers. I'll be here all week. A couple more here, starting with problem number 34. So here's a quick look at the problem 34. So later at home, if you like, you can pause the video and take a little more concentrated look at it. But it gives you all these different isotopes and their half-life. This is not information that you're supposed to have memorized. But these kind of radioactive decays follow the model that we just derived. That initial quantity times e to the kt, etc. So let's understand a little bit about this. Let's see here. So our model, thank you, for exponential growth is this. P equals P sub 0 e to the kt. That's your initial amount, your growth rate or decay rate, time, and your final amount. Just like we mentioned right back here. So let's see what's going on with respect to carbon-14. Carbon-14 is an isotope of carbon. It has 2 extra neutrons in the nucleus, and it's used to help do radiometric dating. Helps you figure out how old things are, assuming that they're less than 40,000 or so years old. Now they tell us in the book, I've got a different figure, but the book says that the half-life of carbon-14 is 5,715 years. That's not a lot to go on, but it's enough. This is going to allow us, Liam, to solve for K. And this is how we do it. Our initial amount is P sub 0. The time is 5,715. K, we don't know, but we do know, at least somewhat, the final amount. Let's think about it. They're giving us the time that it takes this to decay down to half of the original amount. So if we start out with this, whatever it is, we'll end up with 1/2 of that. So that's the big thing here. Not just a 1/2, but 1/2 times P sub 0. Half of whatever this is. It could be 1,000,000, it could be 1,000, whatever it is. Let me fill in the rest of this. 1/2 P sub 0 equals P sub 0 e to the k times 5,715. Our goal, at least initially, is to solve for K. The trick here is to divide out the P sub 0. It's the same on both sides, right? So if you divide out P sub 0, this problem is all of a sudden going to look a lot easier. You're going to be left with 1/2 equals e to the 5,715 times k. And I'm hoping that the rest of that is not too bad. The important step is, did you see what we did with the p sub 0? This is your initial amount. If this was 1,000, then this would be 500. They didn't give us some numbers, so we put in p sub 0, and half of p sub 0. And you end up with this relationship because these cancel out. That's the hard part. That's why I'm pausing here, stalling. To finish this up, ln of 1/2 equals the ln of e to the 5715k. These are opposite functions, inverse functions, so I'm just going to get 5715k is the ln of 1/2. Last but not least, I'll divide by 5715, and that's k. Let's come up with a decimal value for that. So, the ln of 0.5, divided by 5715. So, pretty small. Do you recognize what this is? What's important to notice and not overlook in this number? E to the negative 4. This is in scientific notation. So, negative 1.2128, etc., times 10 to the negative 4th. That's what this is. If you wanted to write it as a decimal, you'd move this 4 places to the left. So there's going to be 3 leading zeros, and then the 12185. Let me just round that to a 9 as your value for k. Our model then overall is p equals p sub 0 e to the negative 0.000129 or 1219 t. That's your model. Let me just do a quick demonstration with this. You don't have to do it yourself. Suppose you started out with 100 grams of carbon-14 found in some old papyrus. How much is going to be left after 5,715 years? So negative 0.0001219 times 5,715. If you were to round that number to the nearest integer, what would that be? 50, which is half of what you started out with. That's why this number represents, the 5,715 represents the half-life. Statistically, I mean, it's just an average. It's about how long it takes, on average, to decay down to half of its original amount. Now, these decays happen at random, so it's not completely precise, but that's what's going on here. Now, there's a little bit more in problem number 34. Let's just pick one part of it. They ask how long or how much of this is going to be left after 10,000 years. So after 10,000 years, actually, you know what? There's a little bit more. Oh, they tell us that 1.6 grams is left. I guess we're going to have to do both parts of this. So there's 2 last parts. After 1,000 years, there's 1.6 grams of this stuff left. So we're going to use that to figure out how much you started out with, and then we can answer whatever question we want from there. This is our final model. After 1,000 years, p sub 0, e to the negative 0.0001219 times 1,000, you get 1.6 grams. Okay. So multiplying by that by 1,000 is going to shift this decimal 3 places to the right. You could do this on your calculator. You don't have to do it in your head or anything like that. There's a negative here still. If I want to solve for p sub 0, all I have to do is divide by this term. So I'm going to get 1.6 divided by e to the negative 0.1219 equals p sub 0. Let's do that on a calculator. You could also bring that up and just do 1.6 times e to the positive exponent. I'll do it with division. E to the negative 0.1219. So you started out with, that doesn't seem to make too much. 1.7? 1.8 grams? Yeah, okay. Yeah, that makes sense. Yeah. So this is approximately 1.8074 grams that you started out with. So that's p sub 0. We can update this model now. This model is no longer just p sub 0. We've got a number that we can put in there. It's our 1.8 something grams. So p equals 1.8074 e to this negative exponent. So that's the second part here. Right here. Finding that initial quantity. That's our 1.8 something. To finish this up, and if you give me the right answer quickly, maybe we don't have to do it exactly. What would I do to find the amount left after 10,000 years? What would I have to do?
Plug 10,000 into T.
Yeah, just plug 10,000 into T. So if you take this model right here, plug in 10,000, that's going to tell you how much is left after 10,000 years. All right, let's call it a day here. Yeah, I know you're disappointed. Try and contain it. For homework, try 1 through 21 and 29 through 33. 1 through 21 and 29 through 33. That's just the odds. That's section 6.2. Have a good week. See ya.